next speaker. Our next speaker is Karthikeyan Vaidyanathan. So, well, when I joined my PhD back in 2011, Karthikeyan was my mentor. So I'm very happy to introduce him. He's a principal AI engineer at Intel. So let me stop sharing so that Karthik.
Yes, can you hear me?
Yes. Okay, hold on for a second. Yeah, can you speak again, please?
Yeah, can you hear me, Hari?
Yes, perfect. So without further ado, let me introduce Karthik. He'll be talking about Habana and their interconnects and how they implement collectives. So I've listened to a different version of this talk in the past. So I'm very interested in seeing what new stuff Karthik has. So Karthik, please take it away.
Right. Thank you so much, Hari, and thank you for giving the opportunity to present here. So let me just share my files. Just let me know when I'm in the full screen mode. Is it looking okay?
Yes, perfect.
Right. Yeah, thank you so much. Yes. So it's it's been what I think 15 years, and so nice to get to a place where all of us meet and have some exciting topics. Especially deep learning is the the new wave right now. All of us are.
Okay. Did I
Going through.
Okay. Karthik, I think we are having some connection issues. Maybe you want to turn your video off?
All excited to talk about what the. Okay.
Karthik?
Yeah. Yes.
Yeah,
Is it better
perfect.
now?
Yes. Perfect. Thank you.
All right. Okay. All right. So let me just quickly jump into the Habana product line. The first generation was Gaudi1. Which has had like 32 gigabytes of memory, and we had 10 Rocky NICs. And we also have the second generation Gaudi2s, which have 24 Rocky NICs and 96 gigabytes of HBM. This is based on 7 nanometer process technology. And I hope many of you have already noticed that the performance, the deep learning performance that we show in Gaudi2 is very competitive for the same process technology that is out there. In some cases, we are showing better. In some cases, we are quite close to the best numbers that you can get for the same product line. So I will focus more on Gaudi2 today. So this is we call this as a HLS2 system. It has 8 Gaudi2 cards. And we have 24 Rocky links that are integrated into these cards. Each card has 24 Rocky links, right? And we separate scale up and scale out ports into 2 components. Scale up is essentially the ports that are used to connect the Gaudis that are inside the server, inside the node. And then we have scale out, which is essentially going out of the node, which goes to the switches, right? So if you see here, on the top, you have these 6 QSFP cables. Basically, these 3 scale out ports from each of these cards get bundled up with other scale out ports that come in, and then they basically go as QSFP cables to the switches, right? And earlier Keith Underwood, thanks to Keith. To making my life easier, because why Ethernet, right? Why Rocky NICs? I think he made enough justification to say why this is interesting. Simply because now these scale out ports can be connected to any Ethernet switch solutions that is out there, right? We don't, of course, we use Arista switches for our scale out solutions, but it it doesn't stop us. And you could use any Ethernet switches that support Rocky. Right. And again, with the scale out, and there's also there is some logic here in terms of the split. Why would we do 21 inside the node and 3 outside the node? And it's fairly simple if you think about it. And I'll touch about why on this a little later. But ultimately, it's a balance between what is the total scale out bandwidth and what is your scale up bandwidth. So because you have 8 cards, you have 8 times 3 scale out, which is 24, and you want to have the similar capacity when one card is talking to 7 other cards, right? And that's the whole logic. And because, we want a pipeline, we want to ensure all the NICs are completely utilized, okay? Okay, now how do we take this and then build our the data center, right? So this is a simple example of how do you build a 128 Gaudi2 system. And you can see that you can just build a fully non-blocking data center just using 3 Arista switches, and you get full bandwidth, right? Meaning each Gaudi in the system can talk to any other Gaudi in the system without any blocking, which means you could basically get full bisection bandwidth, right? And you could, of course, you still need to do scale up and scale out, but you could just build this just using 3 Arista switches. So this is, for somebody who wants to build in the, on-premise, let's say you want to do something smaller scale, you could just do it just using 3 Arista switches, and you can always arrange it in such a way that you can use copper cables for this, right? Now, you could always extend this. I think plenty of people already showed how we do leaf, spine, and core switches, and this is again just a pictorial way of showing how you could build a 512 Gaudi2 data center, or you could extend it to even further, right? But essentially, these are the Gaudi2 servers at the bottom. Then you have leaf switches, which is again the same 3 leaf switches that I showed in the previous picture. And then you could add spine switches, and you could still build a completely non-blocking topology to ensure you get full bisection, and you basically don't get blocked in any particular communication path. Okay, so this is about the hardware. So I will talk about how exactly we went and designed and implemented the software. So at a high level, all our collectives are hierarchical collectives, all meaning all reduce, all to alls, reduce scatters, reduce broadcasts, all of this, right? They all follow this hierarchical pattern. And what does that mean, right? Basically, you have huge amount of bandwidth inside each of these nodes. So you want to first, as much as possible, you want to use the bandwidth that is inside the box before you start sending messages across the boxes. So here is a picture, again, a very high level picture. Each box would first go ahead, do the communication inside the node, and it would, finish the first phase, which we call this as the scale up phase. And then you get to the scale out phase. And if you see, deliberately, I'm showing only the G0s that they talk to other G0s. So, other G0s, you can number them as G8s and G16s and so on. And then you could do a simple algorithm like a pair bus exchange algorithm, and you could do whatever you want to do. You could do all to alls, you could do, any kind of communication, you could get it done as long as G0 is responsible for collecting all the data that is inside the box. And then other G0s just talk to each other and get the job done. Okay. Okay, let's just go through a simple example of how we do this today, right? And maybe for some, for some people, it's probably straightforward, but I want to, highlight some of the challenges, and it's important because, later I will show some results, and you will understand why it's so hard to do this at an excellent efficiency, right? First of all, we cannot make assumptions on address buffers that are used in each of these accelerators. So, and we make no assumptions. We don't assume that the buffer addresses are the same on every accelerator. So, for example, if each accelerator is calling an hcclAllreduce, each accelerator can give its own source buffer and the receive buffer, and they can be different, right? It need not be the same in every accelerator, right? So the first step is to do an address exchange, which is similar to the rendezvous address exchange that plenty of people already touched on it. But it's a very, very important aspect, because if you don't do this, then you cannot perform RDMA operations, which essentially gets us this, we can get the memory copy out of the way and we get excellent performance out of it, but you still need to do address exchange for that. At a high level, we break the all reduce into multiple slices, You could think of it as reduced scatter, and then you also have the remainder. And again, I'm showing just the picture on a single box, where if you the buffers are is arranged like this, then you reduce scatter would essentially get the data. Each process or each Gaudi would own its own portion, and you get the data like this, and then you get to the broadcast phase where P0 is essentially broadcasting this data to other accelerators within the box, right? And we do the same thing across the box as well, right? Just for simplicity, I'm just showing only the inside the box. Now, the point is once you get the data from the accelerator, we have multiple ways of doing the reduction. Of course, we the simplest way, and in the first generation, we did use the SRAMs. So to essentially bring the data from the high bandwidth memory, do the reduction and write it back. Now, why? First of all, again, this is important in multiple reasons. One is you want to ensure that you want to produce reduction values that can be reproducible, right? Meaning if multiple processes are depositing data, you cannot on the fly start doing reductions, because then you cannot ensure the order in which the data is getting accumulated, right? And also the second thing is, because you bring it to to SRAM, you could also save some transactions on the HBM. Okay. All right. Okay. So here's the I guess sort of a 10,000 feet level. I'm sort of summarizing all the optimizations in just one graph, just to show how much we improved, right? The bottom three that you see is the Gaudi1's, the first generation's performance, where the x-axis is bytes here, the y-axis is in megabytes per second. You could sort of see that we were still getting close to I think this is about 95% efficiency from a from a theoretical peak standpoint. We get only from 16 megabytes, and that is all because of some inefficiencies in the way in which this was designed and implemented. Now, one thing I want to highlight is we increased the bandwidth from 85 to close to 262 gigabytes per second bandwidth. That's almost a I think close to 4x bandwidth from an all-reduce standpoint, right? And second, look at the bandwidth efficiency. This is close to 1 megabyte, 2 megabyte message sizes. You get full bandwidth, right? I encourage you to look at other data points from other places. You would see that to achieve this full efficiency at smaller messages. And by the way, we're still improving further. You could see Allgather here, right? Allgather hitting full bandwidth at 256 kilobytes, right? This is with 3 ports. So you could literally think of this as full bandwidth at like, somewhere around 90 kilobytes, right? So this is one is just not bandwidth. Also, the latency is quite, I would say it's quite good. And why is this all important, right? I don't want to go into too much detail, but if you go into these deep learning models, these large language models, you would, very soon realize that you cannot do this on a single accelerator. Then you would do data model and pipeline parallelism, where you're actually splitting the model across multiple accelerators. And when you do that, you start actually exchanging these collectives at a very small size. It's no longer at larger sizes, right? So achieving excellent efficiency at smaller message sizes, it becomes a big deal, because ultimately you get excellent efficiency from the system, right? Okay. How much time do I have?
A few more minutes.
Okay. All right. Okay. I'll skip this. The APIs are fairly, it's out there, but I do want to highlight that again, Gaudi2 numbers are already, you can look at in the MLPerf website as well as in our website. first thing you can see that, up until 32 devices, we get very, very, excellent efficiency, mainly because of the way that this was orchestrated, the AllReduce calls that are getting used in these neural networks like ResNet and BERT, especially BERT. If you think about BERT, I think it's about 660 megabytes. So you're really talking about 1.2 gigabytes of data transfer on the network. And you're, from an efficiency standpoint, we're finishing in the order of 5 milliseconds, right? So that's that's the order in which we are talking about. And that's the reason why we get excellent scaling efficiency. Needless to mention, the compute efficiency is also good. As I said, the compute performance is very competitive from, in terms of, I think the BERT numbers are either matching or even beating what's out there, right? And even ResNets are also, fairly competitive. We also have, stable diffusion training. We are getting excellent efficiency, and we continue to show, excellent, and this was done on 64 cards. We are doing the work for, a few hundreds of cards. It's, and just wanted to highlight that the communication efficiency that was shown before, we continue to see, good efficiency even at this scale. Which again, all of this will help in getting excellent efficiency. If someone is interested in looking at, I did show only 3 neural networks, but we do have, encourage you to go to the website. We have a lot of neural network models running, across both PyTorch and TensorFlow. You can feel free to look at the performance. I guess, yeah, that's all I had. Any questions, I'll be happy to take.
Let's thank the speaker. We have time for one quick question if there is any. If not, thanks a lot, Karthik.